Okay, well, good morning, everybody. I shall start by thanking the organizers for this nice meeting and the occasion to talk here. The work I'm talking about has been done in collaboration, and two of the main collaborators are here, so Nicolas and Giorgio. Also very important collaborators were Nikos Fytas and Marco Picco, who are unfortunately not here. So how do you like this thing? Okay. Okay. I cannot see it. Okay. Yes, this is the thing. Okay, so the plan of the talk will be the following. Of course, the random field Ising model is a very well-known model, so I'll give a short introduction. Then we have some new ingredients in the way we study these things, so I'll explain them. And then we'll address the main problems here, which are universality, dimensional reduction, and maybe supersymmetry. Okay, so everybody know the standard Ising model in which we have spins on a lattice, which may have some nearest neighbor interaction, which in this case is ferromagnetic, meaning that the spins want to point along the same direction, and maybe there's an interaction with the external field. Now, if we want to disorder these things, we can do it in many ways. We can disorder the random fields, we can disorder the couplings, we can even introduce dilution, but we're not doing anything so complicated now. This was done in the first two talks, but now I shall keep the exchange interaction simple with no disorder, and we only have disorder on the random fields. Okay, so the energy contains two P's, the standard one, which is just like in a clean system, no disorder, and the magnetic field, which introduced the randomness. The model has been useful in the study of many simples, such as diluted antiferromagnetic and many other systems. But okay, let us discuss the main properties. We know that in the absence of any disorder, at least about one dimension, the system is ordered at very low temperatures. So one may ask what happens when you introduce the disorder, and the thing was answered by Imre and Ma a long time ago. The argument runs as follows. So imagine that you are at very low temperature in a ferromagnetic background, and you reverse the droplet of a droplet of spins. You change the sign in a coherent way for all the spins in the droplet. Now you will pay a surface price because of the interactions which are broken in the boundary of the droplet, and you may eventually gain some energy through the interaction with the random field. Now the central limit term will tell you that the gain, the eventual gain, will be of the order or the radius of the droplet down up to the power t half. So if the dimension is high enough, clearly the energy price is going to be too high, and you do not want to reverse the droplet. On the other hand, if the dimension is low enough, the two terms can balance, and you may lose the ordering. So this is an indication that the lower critical dimension will be 2. Okay? On the other hand, the mean field analysis tell us that the upper critical dimension is 6. So, in principle, the range of dimensions we're interested in is from 3 to 5. Of course, one can study things at the lower critical dimension. Luca and Giorgio has done similar things recently. But, okay, we shall concentrate on that range, from 3 to 6. Okay, one can put forward a randomization group analysis, which has been by people in the room, by Moore. And the phase diagram is as follows. In the absence of any disorder, sigma quantifies the disorder. It is the variance of the random fields. So in the absence of any disorder, we have the standard ferromagnetic transition. On the other hand, at low temperature, for very small disorder, about 2 dimensions, we expect to have a ferromagnetic phase. And if the disorder is very high, eventually we find a paramagnetic phase again. So we have a phase transition here. The normalization group flows from the pure model to that fixed point here. So this is the relevant one. In the analysis, one finds that there are 2 important correlation functions, the connected one and the disconnected one, and each of those define their own anomalous dimension. The standard one connected to the linear response is named eta, and the one connected to the disconnected correlation function is the bar eta. Okay? We also know that there are violations to hyperscaling due to this zero temperature fixed point. So we have a very unusual fixed point at zero temperature, which do not depend on two critical exponents as usual, but in principle there are three independent critical exponents, the thermal one, and the anomalous dimension, and bar eta. However, the hypothesis has been put forward that the eta is just half of the bar eta, so indeed there is only two independent exponents. Okay? The problem has been also studied by the perturbative renormalization group, and as far as I know, the first person who found the phenomenon of dimensional rotation was Peter John. I don't know, but I think he was. So dimensional rotation means that the critical exponent of the random field Ising model in dimension D coincides exactly with the critical exponents for the standard pure Ising model, for magnetic Ising model, in two lower in D minus 2 spatial dimensions, okay? And also the two critical, anomalous dimensions coincide. A few years, rather soon after this discovery, Giorgio and Nicolas found that there is a hidden supersymmetry in the problem. And the hidden supersymmetry makes the dimensional rotation robust to all orders in perturbation theory. So we know there is a problem because the random field Ising model in 3 dimensions orders, while the Ising model in 1 dimension do not order at any finite temperature. So something is clearly wrong with perturbation theory for at least for one of those dimensions, C, okay? So those are the questions, here go the questions we were going to try to discuss today. Because perturbation theory cannot be trusted, even if followed to infinite order, in principle, every prediction from perturbation, the perturbative renormalization group can be questioned. In particular, universality. Universality has been questioned many times, rather recently even, by massive simulations. Universality in the sense that one usually assumes that the particular distribution for the random, statistical distribution for the random films is not very relevant. Any distribution is as good as any other, at least if the variance of the distribution is finite, of course. Well, many papers along the years have found violations of the universality in the sense that different distributions do not give the same critical exponents. Also, one can question about dimensional reduction, and finally about supersymmetry itself, which seems to be the support for dimensional rotation. In order to address this question, we shall be using numerical methods, okay? Which I'll now discuss in not many details, but a little bit.
Just mention the rigorous results on random field Ising.
Well.
Ingrid and
yes.
The history on this is very relevant, right?
I mean, the rigorous results are in favor of the Ingrid-Mar lower critical dimension, which of course conflicts with dimensional reduction.
Sure, but I don't get the point.
I mean, if you use dimensional reduction, you would have no transition in 3 dimensions.
Yes.
Yes.
You haven't mentioned the rigorous results.
Yeah.
I'm asking you to mention.
Well.
That's not. I mean, Ingrid-Mar is not rigorous.
Oh yes, I know, but I know that there are 3 results showing that in 3 dimensions there is ordering. Yes, of course. Well, this is a short introduction. I apologize.
No, but it's absolutely crucial.
Those are very important results. Those are extremely important.
Okay, I'm sorry. I'm sorry.
For the interface models, the dimensional reduction supersymmetry is wrong to leading order in epsilon and violates rigorous balance. The leading order is not the small order.
Okay, but you mean dimension 3, okay? We are talking about dimension 3 always, right?
No. Here's coming out of 6 dimensions.
Okay, but I'm talking now about the random field, okay? Okay. Now, let us talk about things. I'm supposed to talk about these things in 25 minutes, please.
But it was solved, this problem was solved years ago, right? So why don't you mention that?
Well, I'm mentioning you in the last slide. What is that?
Perhaps you can mention at the end if you have still some time.
Just, okay. Well, I apologize to everybody if I'm not putting somebody important work. Anyway, because we have a questioning of universality, we're asking about different disorder distributions. We shall be using different disorder distributions because the claims have been that different disorder distributions produce different critical exponents. Okay? So in particular, the things we have been considering are Poisson distributed random fields or double Gaussians. Double Gaussian are sketched here, means just two Gaussians superimposed, slightly separate, which somewhat interpolate between excuse me, a bimodal distribution and the pure Gaussian distribution that we typically use. Okay. The second thing is that we shall be working exactly at zero temperature. We need to find the ground state, and this can be done using a graph theoretical algorithm. This thing has many advantages. On the first one is that the relevant Phys point is exactly at zero temperature. Okay, so this should somewhat clear the analysis. Next, finding the equilibrium state is no more an issue because you just find the ground state. You have an algorithm which is sure to provide the true ground state, so equilibration is not an issue. And then you don't need to average over the thermal noise to have the result there. Okay, so the advantage, of course, is that given this relatively simple algorithm, you can reach larger system size with the standard Monte Carlo. And by larger, I mean the following. Using Monte Carlo at finite temperature, you rarely go above lattice size 32. In this way, you can get lattice sizes larger than 192 in 3 dimensions, 60 in 4 dimensions, or 28 in 5 dimensions. Also, in order to get very accurate results, we do a large number of realization or samples of the random fields, of the order of 10 millions of those. Just, I give here some comparison with the other works. Next, because we are working at zero temperature, we have to solve problems which are specific of zero temperature, in particular the computation of the connected correlation function. The point is that the connected correlation function you typically compute in this way, and this is 0 at exactly zero temperature, because there is only one spin configuration at zero temperature, which is the ground state. Okay? We bypass that by using the linear response. And the linear response, you can compute it by correlating the spins in the ground state with the random fields. Okay? This was something that was known a long time ago, but can be generalized to other random field distribution. I mean, this particular formula is specific to the Gaussian distribution, but you can generalize that to the other distribution. Also, you can introduce reweighting. Reweighting means that you do a large scale simulation for a given value of the parameters of the disordered distribution, say the width, sigma, and from those values you extrapolate to nearby values of sigma. Of course, you can check that, this extrapolation, just by, say, performing a large extrapolation simulation here, and then just extrapolate, here, and then you extrapolate to that point, and then perform new simulation just at that point, high accuracy one, and then you can check whether the extrapolation is trustworthy or not. And it is. I mean, these are simple to discriminate. In this way, you can also compute, of course, you can reweight, you can compute sigma derivatives. You completely solve the zero measure syndrome, and you can compute derivatives. The next ingredient in the approach is studying finite scaling using finite scaling. So how it works? We shall be working with the quotient method, which is some sort of phenomenological renormalization. Okay, so consider first a dimension-full quantity. The dimension-full, I mean something which has a non-trivial critical exponent, XO, a quantity which diverges in the thermodynamic limit with some critical exponent. If we sit ourselves exactly at the critical point, that quantity will scale as a power of the system size. And the scaling dimension will be the critical exponent divided by nu. If you depart slightly from the critical point, the dependence is given by the term here in the parentheses. You have a function, a scaling function, in which we have the distance to the critical point rescaled by the power of the system size, and the power is known to be 1 over nu. There are, of course, corrections to that formula in the form of power law decreasing terms, which are controlled by the leading correction to scaling exponent, which is the value of the beta function at the fixed point, the derivative of the beta function at the fixed point. The kind of dimension-full quantities we typically consider are those. We have the order parameter density, and also we have both the connected and disconnected propagators, which are studied in real and Fourier space. For low values of the wave vector, even 0 values, we know that the scaling dimension is just 4 minus bar eta, which is the scaling dimension. For the connected propagator, instead, the scaling dimension is 2 minus eta. And we can also take ratios of both in order to control the difference of the two anomalous dimensions. For dimensionless quantities, an example of those are here. We have the Binder ratio that was discussed by Juan in his talk, and also the correlation length in units of the system size, correlation length that we compute using the second momentum formula. We had those for both for connected or disconnected quantities, okay? And these quantities are simpler in the sense that there is no divergent prefactor. We only have the sigma dependence here, which is given in the form as a standard finite scaling form. Okay, we had the distance to the critical point, the scale by this factor L to the 1 over nu. Now, what we do is to seek for values of sigma such that the dimensionless quantity is the same in two system sizes. For instance, L and 2L. Now, you use this formula here, and for a minute disregard this correction to scaling. You immediately realize that the crossing may happen only at the critical point. Of course, corrections to scaling cause small departures from the critical point, but this can only happen here, okay? So here's an example of how it works for the Gaussian random field in 4 dimensions. We had the connected correlation length in unit of the system size as a function of sigma, and we look for pairs, 6 and 12, 16 and 32, or whatever, okay? So we see that there are crossing points that shift a bit with the system size, but they converge very fast to the critical point. In fact, one can easily work out that the correction to scaling are of this order, are inverse power of the system size, and the correct exponent is here, so omega plus 1 over nu. Now, if you evaluate the dimensionless quantity exactly at the crossing point, you get a universal quantity, something which is universal with respect to chance, or should be universal. You can also compare dimensionful quantities by taking the ratio of the value exactly at the crossing point. And the ratio will be 2, which is the ratio of sizes, to the power to the scaling dimension. Of course, there are always scaling corrections here. Now, a very important ingredient here is to beware of subleading scaling corrections. And this is an example which I personally consider spectacular. It is the Binder cumulant at the crossing point for the 4-dimensional random field Ising model. Okay? Data here are shown both for the Gaussian random fields and for Poisson random fields. As you see, there is a transient behavior for large system sizes in which the two seem to be completely different. And there seems to be no size evolution here at all. So this line here corresponds to the pair 1632. If you were given only the data corresponding to sizes smaller than 32, I guess that most people in the audience would conclude that there is an universality violation, because clearly this will be the limit, the infinite size limit. This will be the infinite size limit because there is no more any size evolution, and the limits will be clearly different. But see what happens when you go to still larger lattices. So corrections to scaling, particularly leading corrections to scaling, is a very complex development. There are many different kind of terms. And Andrea Pellisetto, who is not here, but he's a real expert on the thing. Anyway, can induce rather complex behavior. So how we try to control that? What we do is we make an explicit assumption. We assume universality. We assume that in the limit of infinite size, there will be universality, and the extrapolation to infinite size will be the same for every distribution. Okay? This assumption we control as in standard statistics through a chi-square test. Okay? We perform a fit in which data from different distributions should have the same limit. Scaling corrections take the form of a low-order polynomial in the leader term. The lower the order, the happier we are, of course. And also, it is very important to keep in mind that very small system sizes should not be trusted. Okay? So we impose a cutoff, a minimum size. We only start considering system sizes from some minimal size on. Okay, this program has been carried out in 3 dimensions, 4 dimensions, and 5 dimensions, more or less successfully. In the case of 3 dimensions, for instance, it's rather spectacular to see here what happens to the double peak distribution. In the case that the peaks are very thin, this is the case of very small peak width. This is the red points here. As you see, for a small system sizes, I'm plotting the results here as an inverse function of as a function of the inverse system size. In the case of the small system sizes, one has the impression of having a very strong universality violation. But if you push by studying larger and larger systems, things eventually converge to the universal limit. Okay? So we are more or less convinced, at least as much as you can let yourself be convinced by numerics, that there is universality in the problem. At least this holds. What about dimensional reduction? Okay, I'm comparing here the numerical values of the critical exponent that we get for the random field in 3 dimensions, 4 dimensions, 5 dimensions. Okay? You also have to compare here the mean field, and then there is nobody in the world of the pure Ising model to which you can compare the 3D results. But then you can make comparisons between 4D and the 2-dimensional pure Ising model, or 5D and the pure Ising model in 3 dimensions. Of course, 6D will be pointless because there is mean field in both ways. Okay? And if we have a look, for instance, to the thermal exponents nu, we observe, of course, as we increase the dimension, we approach the mean field limit, 1/2. And if we make the comparison, it is clear that the dimensional reduction is off by many standard deviations in 4 dimensions. Okay? But in 5 dimensions, at least with this numerical accuracy, things are compatible. This is much clearer for the new exponent than for the anomalous dimension, because the anomalous dimensions are small, so that the relative errors are large. But anyway, if we perform an explicit chi-square test assuming dimensional reduction in 5 dimensions, to this accuracy, the results hold. So what about supersymmetry now? Okay, we know that supersymmetry implies dimensional reduction. So if we have no dimensional reduction, there is no point in seeking supersymmetry. Okay, you can do it just as a test if you wish, but it's clear that you're not going to find it. Okay, so this immediately discards 3 and 4 dimensions.
So can you define what supersymmetry means as far as observables?
Yes, I will do in a minute. I will do in a minute. Okay? As I said, 5 dimensions is more promising. So in 5 dimensions, because at least numerics are consistent with dimensional reduction, one can wonder about supersymmetry. And then we have recently published a paper with Nicolas, Giorgio, and Marco, in which we explain how to do it in great detail. So the point is the following. Okay, we take a point in the 5-dimensional lattice. So we have the coordinates corresponding to the first 3 dimensions, x, y, and z. X, y, and z. Sorry, Italian is terrible for that. X, y, and z. And then we have the 2-dimensional manifold of T and U. Okay? And we shall be considering an asymmetric lattice in which we have a common length or size for the first 3 dimensions, x, y, and z. And then we have a different size, larger, with an aspect ratio r for the 4th and the 5th dimension. Okay? Now, if we just take the limit of infinite sides in all dimensions, we have a supersymmetry with a supergroup which is 052. The 5 corresponds to the spatial rotation in 5 dimensions, then the 2 corresponds to the supersymmetry. However, what we do is something different. We take explicitly the limit of infinite r, infinite aspect ratio. Okay? In this way, we have a reduced rotational symmetry only for the T and U dimension, T and U coordinates, only on those dimensions. This happens, of course, because the spectral gap is of order 1/L. So the limit can be reached. The convergence to equilibrium should be exponential in R. And then, because the gap is anyway very small, we recover the rotational recovery, but only along the infinite dimension, which are T and U. Okay? So which are the consequences of O22 group? First, if we compute correlation function, here is only the case of 2 points correlation function, but we can also check 4 points correlation function in the paper. In a very particular way, the correlation function on the random field corresponds to correlation function on the pure Ising model, okay? Which is a particular way. You can take different points for the correlation along the x, y, and z dimensions, but the u, t, and u dimension should be the same. U is fixed in both points. So you could take 2 points exactly in this way, same t and u coordinates. You can may vary x, y, and z. Then those correlation functions should be the same. This is the prediction, should be the same as those of x1 for the pure Ising model. And what about the connected correlation function? In the connected correlation function, we have a word identity. For the connected correlation function, we have a word identity that connects the connected correlation function with the derivative with respect to rho square. Rho square, recall, is that rotational invariant magnitude for all the disconnected correlation function. Now you can take the integral of that equation by summing over all values of the t and u coordinates. And the conclusion is, from the first line here, that this new integrated correlation function is also proportional to the correlation function of the pure Ising model. Okay? These zeta here are constants, are constant values. So you have more examples here. We'll just discuss shortly an example which regards the word identity. You can check these things. As you see, the first thing is that you can, I'm plotting here the correlation function as computed by this integrated K correlator in unit of the system size. And this is represented as an inverse power with exponent omega taken from the 3-dimensional Ising model for different aspect ratios. As you see, as we expected, the limit of infinite R is reached very fast. We were expecting an exponential convergence in R, uniform in L. And this seems to be more or less true. Also, you can then, once you have reached the limit of infinite R, you can try to extrapolate to infinite L. And by so doing, we get this number, which can be compared. It has an accuracy which is of the order 1%, which is completely compatible with the 3D counterpart. But this is just one example. You can see, you can check more of those coincidences in the paper. So this is time for some conclusion. Well, we have introduced a new technology for the simulation of the random field Ising model. Of course, the graph theoretical algorithms were known, but the fluctuation dissipation analysis and the finite data scaling, I dare to say, is our idea, which has increased enormously the accuracy in the studies of the random field Ising model. The numerics are centrally consistent with universality. And about dimensional reduction, I should say that our results are consistent with the dimensional reduction in 5 dimensions, but not in 3 and 4. Now there are some open questions. So which are the physical, my understanding is 2 of those are, which is the physical mechanism that really breaks the supersymmetry or perturbation theory? And then that supersymmetry holds exactly, not to some accuracy, but exactly for some dimensions below 6. And here we have diverging views. On the one hand, there are some arguments, mostly by Giorgio and Doxenko, which expect tiny violations, very, very small violations, which can get large only well below 6 dimensions, but they should be present for any dimension below 6. On the other hand, we had the work by the group by Targis, and I apologize for not quoting you before now, using the functional Renormalization Group, which do support the existence of some dimensional range in which we have a supersymmetry. We really have an exact supersymmetry. There is a spontaneous breaking of the supersymmetry at some intermediate dimension, which they say is very close to 5. Okay, and as far as I can tell, I will say that the question is open. So thank you for your attention. I apologize again for not quoting everybody.
Maybe I didn't follow in detail your argument, but does the supersymmetry reflect on some symmetry of the transfer matrix? And if so, when it is broken, I guess in 3 and 4 it is spontaneously broken. Does it reflect on the spectrum of the transfer matrix? I guess that this is...
Sorry, I cannot answer that question. I don't know.
Just one comment on the physical mechanism. Well, first, I think that's the question is not open except if you don't believe our answers. But the physical mechanism is due to shocks or avalanches, right, that are present at 0 temperature in disordered systems. And the shock or the avalanches are subdominant between 6 and 5.1, and they become dominant below 5.1. And then that breaks the supersymmetry, the dimensional reduction, because the word identity then blows up and is no longer satisfied. So I think we have a pretty good handle of what's the physical mechanism and how everything behaves between 6 and 5. But
Okay. Daniel?
I said 2 comments. One was on the dimensional reduction and supersymmetry thing generally. So for the problem of an interface in an Ising model, there is a result dimensional reduction also. And that's violated the leading order in epsilon. And there's a simple mechanism. The renormalization group flows just take you out of the region where the supersymmetry would be right. And so this, I don't know if that's a physical mechanism, but it's the fact, a renormalization group description of these systems is a better one than formal descriptions. So that's one comment. The second comment is about universality and estimates of critical X models. So the only really compelling experimental evidence for universality in any system is in superfluid helium, so 3-dimensional XY model. And there, I've forgotten what they go down to 10 to the minus 7, reduced temperature, something like that. And if you look at the behavior as a function of pressure, you find the critical exponents all depend on pressure. So you would think it's not universal. And then you put in corrections to scaling, and they become universal. But if you ask about errors on exponents, the errors on the exponents going in that close are, I think, probably still bigger than the ones you're quoting here. So I think one should be very skeptical about exponents inferred to this accuracy in pretty small systems.
I would like to make a historical comment. So usually people give reference, start and give a reference to Imri and Ma. Yes, but in fact the first paper talking about dimensional reduction in the random field Ising model was by Gérard Toulouse and Lacour-Gaillet. And they did it for the spherical model. And Imri and Ma, this motivated Imri and Ma, and they give reference to Toulouse and Lacour-Gaillet. So this was somehow intuitive approach. But there has been then a paper by Marc Mézard for the spherical model, and they proved that for the spherical model, it's known that we have dimensional reduction. Now, so there have been speculations, I don't know, what happens to ON models. And I think because you have one case, the Ising model, and the other hand, you have the spherical model, so what happens for N between? And I think there was a paper by Peter and Marc Mézard. But not many people have worked on this direction. So that was my remark, which was just a historical remark.
Okay, thank you.
Okay, well, thank you. All the final answers will be at RSP AD. But thank you.